So in the second part of this JWebbinar, I'm going to talk about the second and third levels of the pipeline. So once you have the notebook and you run it offline, for instance, you will need to download data. There is a link provided with all the necessary data that you need to download just once. You can, once you do the download, you will have two folders, one with the input data and one with the results. In the input data, you can either include the data or you may just use some of the data available on the mast. It's up to you. So I will skip the first step, which has been configured only for this JWebbinar, but actually the copy that you will have will just allow you to download the data. And then in the next one, I'm just importing all the necessary. Actually, some of them may be a little redundant, but most of them are used in this notebook. So the notebook can be run for NRS1, which is the first detector, and it can be run also for the second detector. So you have to run this once per detector. You also have two options for run. In the first option, you can do load, and in this case, actually the first is process. If you opt to run in process mode, what will happen is you will actually run every cell, and the result will be stored in your local directory. So then if you decide to run it in load mode, even if you haven't run it in process mode, you just load pre-processed data, and you will have the plots and results on screen for faster information. Now, one thing I have to mention is that right now, if we go and run all the necessary steps in Spec 2 of the pipeline, or TSO 3, which is the third level of the pipeline, we will get some products, but unfortunately, they won't be as good and as optimal we wish for our light curve fitting. So for that reason, I'm going to skip most of those steps, but offer you workarounds, which I call steps 1 to step 8. Once in the future, when the pipeline is completed, at least the Spec 2 and the TSO 3, for the purposes of time series observations, and if there is a wish for that, we will show in another JWebbinar actually the same notebook with the exact STSI pipeline steps. But for now, we're going to do our workarounds, except for one step, which I'm going to talk about, and get the spectroscopic light curves and the white light curve, including fitting parameters. So before we start, we can load one of the ratings files. We will read it as a data model, and we can plot to see what's its contents. So here, for instance, you can see the individual integrations. So you can see that they are almost identical. There are small differences between them owing to the different 1/f noise, which is an imprint of the detector readout electronics on the individual integrations. Actually, when you read with a data model, which is shown here, if you just say rate ints, which is my rating contents from the data model, and if you say .info, you would actually see many lines of its contents. But actually, if you want to see the full contents, you can just say max rows equals none. And then if you run this, you will get the entire content. So basically all the information that you may wish to access. And if you are curious to see what it contains, it's actually a lot of data. Okay, so now that we know what the data models of the rate ints contains and how it looks, we can go into the individual steps. So before I offer you the workarounds, with the exception of the first step from the pipeline, let me go into the 8 steps that the pipeline is supposed to do in Spec 2. So these are assigning a world coordinate system. It's called WCS. So in the context of an image analysis, the pipeline would assign the array and dec, right, ascension declination information for your field of view. But in the context of spectroscopic observations, that would be information about the wavelengths of your spectra along the detector. So it's a wavelength map. So that step is important for us. Then the pipeline, what usually does is it extracts 2D spectral cutouts. These spectral cutouts are basically just reduced sub-images of your rate ints. It does that for saving memory and for manipulating working with a smaller amount of data, which can reduce the computational demands. Then it performs flood fielding. We're going to skip these steps again. Then it does assigning source type, photometric calibration. At this step, basically, you convert your spectra, you place your spectra on an absolute scale so that each pixel, the flux of each pixel, for instance, is converted from counts per second to physical units. Then you have pixel replace, which we will include in our analysis. Pixel replace basically takes care of any pixels which have a flag that indicates that they are, for instance, bad, dead, with low response or something like this, with any general problems. And then step number 7 from the designed pipeline from STSI is actually the reason why we can't run at this point. The resampling step basically takes the spectra and corrects for this curvature here by putting them in a new array, so to speak, where the spectra would be rectified. So this step at this point is not working, and once it's resolved, we can actually go ahead, test, and see how much the resampling, for instance, would affect observations, for instance, for time series observations, because it basically the pipeline takes a general approach for all observing modes and aims to have a so-called uniform approach into the reduction and analysis of the data from all modes. So for our case, for time series observations, we don't do any resampling. And then finally, the pipeline is supposed to use this resampled spectra and perform a simple spectral extraction, which actually just takes, it sums the flux within an aperture as it runs along a row, the mid row, basically, the mid row of the 2D images, the ratings. Okay, so let's go and take a look at the individual 8 workarounds, excluding the assign world coordinate system step. In the first step, what we do is we run the pipeline and we obtain the wavelength solution for one of our segments. And once we run this, it usually goes quite fast, only for about 10 seconds, at least on my computer. You can then obtain the wavelength map, and here is how it looks for NRS1. So for each detector column from 0 to 248, you have assigned wavelength solution, which is color coded on this plot. So you can see the individual wavelengths running from 2 point something to around 4 microns from left to right. So we will use this map later on when we extract the spectra to assign wavelengths to each individual column. So we will save this, and then in the second step, what we do is, since we have only 3 segments of ratings, we can actually read the individual ones and just put them in big array. So we will have in one 3-dimensional array all the rate ints from the 3 individual segments. So this would be actually the not only the ratings, not only the 2D spectra, but also the error, the data quality arrays. And we also can access the timestamps from each segment. These come as array for each segment. So we obtain also the timing information for our integrations. So this would be useful to easier handle and work with the data. Now, one thing you may consider is that if you work on other data sets, especially some of the very few data sets where we have observations of very bright sources consisting of only two groups, say, per integration, you may end up with very large number of segments. So here we have just 3, but you may have cases such as observations of HD 189 or 209, where you may have like 20 something segments. In that case, if you actually work this way, you may enter into a memory issue. So that's why you may wish to use this only for a few segments. But for this data set of 3 segments, it's perfectly fine. Before we continue, we actually can go ahead and plot the individual timestamps as function of integration. The reason why we do this plot is just a quick sanity check if the timestamps have been calculated by the ground system when the data has been received from the telescope in the correct order. We have found, for instance, during commissioning that some of the data sets, at least during commissioning, they have been affected by issues with the calculation of the timestamps. And in such cases, instead of seeing this plot just as a perfect line, you may see actually different segments where you have different slopes for those segments. So this plot right now just shows that everything is fine. Okay, so next, what we do is we define a lower and a higher pixel for between which we will obtain the data. So we will trim and not continue our analysis with the data that is lower than around 600 and something and 2000 and something. So we will just use the section of the rate ints where the spectra have high signal to noise. And once we do this, we basically just have the data with the high signal to noise of the spectra. And we do the same cutout also for the wavelength solution. Okay, now that we have all this, we can just go ahead and save it. And if we run in load mode, it will just load. For this notebook, I also include removal of 1/f noise because currently the pipeline doesn't have 1/f noise removal at stage 1. Now, there are different debates about where the removal of 1/f noise should occur. So for this notebook, I just assume that the data that you have has not been corrected for 1/f noise. So when you run this notebook for Spec 2, you can opt to include that step, or simply you can not include it. In case 1/f has been removed in Detector 1 and you continue by removing it here, you probably remove it twice, but it may actually have very, very small effect on your data. The way that 1/f noise is removed here, so basically what I do is I run along the dispersion axis, which is the horizontal axis of the data, and I define background regions which are away from the pixels which have the spectrum, and I take the median flux value in these background regions, and I just subtract that median value from the entire column. So this is done by this function, correct 1/f. This is a very simple function, and it takes very little time, probably like 20 seconds. And if you run that step, you can see it will produce here this 3-panel plot. So in the first panel, you can see the uncorrected data. In the second panel, you can see the corrected data. And then in the third panel, you can see the difference. So basically, the difference just shows you in an easier way these stripes which are characteristic of the 1/f noise. Now, one thing I need to mention is that the plans for the further development of the STSI pipeline is to include 1/f noise correction at Spec 2. It's called NSClean, which will become available probably during 2024. It's going to be an optional step for run, so you will have the choice. It won't run by default. The data on the mast won't be corrected for 1/f noise, but if you opt to reanalyze your data, you can rerun it with the NSClean algorithm. Okay, so now we have corrected our data for 1/f noise. We can go ahead and save this intermediate step and continue to the next one. So in the next one, what we are going to do is, assuming Detector 1 level issues with the individual pixels have survived, we would need to do a correction for these pixels. So the problematic pixels are seen here as these bright ones, but there are also cases where you have also dark pixels, which are visible, for instance, here in the corrected 1/f corrected spectrum. So to do this, we actually make use of an approach which has been developed and done for HST observations. So basically the idea is the following. If we have affected pixels by, say, if some of our pixels are dead, or if they have low response, or if they are hot, then what we can do is we can identify those pixels and make use of the data to actually produce a correction. The idea is the following. Basically, say that we have one column, for instance, the column that contains these several bad pixels here. What we can do is we can take a few columns before that column and a few columns after that column. And we can, if we know which pixels are affected, we can just ignore them and then median combine these few columns, these adjacent columns, by taking the median on a row by row basis. So that would produce a profile which will have the flux values for each of the pixels in a column. So if we know the pixel indices of the affected pixels, we can just replace our affected pixels with the flux with the flux of the pixel from the nominal PSF profile. So this procedure has been detailed in this paper in 2014. It has been found to work very well for HST data. And actually, I have tested it also for this data, and it works great. So I'm providing here the necessary functions that do this. And basically, once you run this, it will do the identification correction, will save the results, and then we'll produce this plot, two-panel plot, where you can have how the data look before the correction and how the data looks after the correction. Now, you have to play a little bit for individual data sets with the number of columns you wish to combine. For instance, you can use 3, 4. Just keep in mind that this usually is half of the number. So basically, if you say three columns to be combined, that means 3 before the affected column and 3 after the affected column, so a total of 6. One drawback that you can imagine is that, for instance, if you define 2 wide windows and you have like spectra which have curvature, you may end up having some issues. But for small numbers like between 3 and 5, it should be all right. Okay, so now that we have corrected our spectra for the bad columns, for the bad pixels, also non-pixels. Oh, one thing I forgot to mention is that some of the pixels may turn out to be, with very low or very high value. For instance, a missed cosmic ray. but may not be identified by the pipeline. So you can actually use this nominal PSF profile, and just by taking the difference between the column that you inspect and the nominal PSF profile, you can easily identify pixels below or above certain threshold. I'm actually doing this in the function, so this is taken into account. But you can, if you wish to exclude that part, it's also an option. Okay, so now in the next step, what we need to do is we need to identify where our spectrum is exactly located. We see it by eye, but what we can do is we can run along the dispersion axis and take each column again. And for each column, we can fit a Gaussian profile to basically to the profile of the spectrum, the spatial profile of the spectrum. This is the most time-consuming step in this notebook, so expect between 15 and 20 minutes depending on your computer and on the data set that you use. For instance, for NRS1 it's about 15 minutes, for NRS2 it's about 20 minutes. Since JWST data is very good in a way that the spectra are basically kept always nearly at the same position of the detector, you can also do a median combination of all your data, and you can make use of that median combined image to do the spectral tracing just once. That's also an option, but and it's included in the notebook. But for the sake of looking at additional complementary data, which can be used for further analysis, I'm actually running not on the median, but on the individual images. And so when it runs on the individual two-dimensional spectra, basically, you will get for each column one measurement of the position, full width half max, and you will save this information for the entire spectrum. So these are 1,300 and something columns for about 400 and something spectra. So it's a lot of data. And you keep this data, basically the notebook will save it here, or will load it if you downloaded the pre-processed data. Now, having the scent reading information, what we can do is we can do the spectral tracing. And the spectral tracing, basically what it does is it takes the locations of the centers of the Gaussian fits for each column again per spectrum, and then it would fit a polynomial for each two-dimensional spectrum to locate where, basically just finds a smoother function which traces the extent of your spectrum. And that step is very fast. So once we have that, we can then save this information and go ahead and use the centroid information. Remember that for the centroid information, we have it for each column. So if we want to have an overall measurement of, say, the full width half max for each spectrum, we can actually use all the full width half max measurements, say, either from the entire spectrum or between specific pixels, which also correspond to specific wavelengths, and just take their median value. And that's what we do here. In this step, we take the median values for the entire spectra, for the full width half max, and for the mean position of the spectrum. Basically, it would correspond to what row the spectrum, with respect to what average row the spectrum is. And so if we plot this, you can, as a function of time, remember that we also have the int times arrays. So instead of plotting the median full width half max as a function of the individual integration, which is also a solution, we plotted versus time. And now here we have 3-panel plot. In the first panel, we can see the median full width half max as a function of time, and we can see that it's basically separated in two parts. there is a jump between the first and the second part, and you may wonder what this may have been. So basically, since JWST is an observatory consisting of an open mirror in space, it's actually, it can be affected by anything that flies and is on the path of the mirror. For instance, micrometeorites, which are small particles which can bombard the surface of the mirror. Since the mirror is not monolithic but is segmented, when a micrometeorite hits one of the segments, it can actually affect its orientation. You probably know that these segments on the mirror can be articulated at specific positions so that they collectively make a surface, which basically is the surface of the telescope mirror. But when a micrometeorite hits one of those segments, it can actually put it out of alignment. And so, since these micrometeorites can make very small changes, these changes can actually become the reason why you have different full width half max before a micrometeorite hit and after a micrometeorite hit. And the time series observations are very good actually and sensitive to detecting such events. And here we have one such example, just a couple of tens of minutes after the mid-exposure, which also corresponds roughly to the mid-transit event, we had a micrometeorite which hit one of the segments and caused this change in the full width half max. So for any of your observations in the future, when you analyze, you may wish to plot the full width half max. And actually, I would say every parameter from your spectral tracing can show some such information. It's not in every data set because the so-called tilt events, uncommanded change in the orientation of the individual segments, they come in different flavors. For instance, since in this case of both time series observations, we're looking at spectroscopic time series, we can't have an idea from imaging data what is happening. But for instance, for NIRCam data, where you would have also imaging data, you could see actually what changes can occur before and after a tilt event. In this case, for spectroscopic data, full width half max can be a sensitive probe for some of the biggest probably tilt events, but for small ones, it's very hard. Okay, along with the full width half max, we also plot the median position of the spectra in the vertical position, and we can also use the fitted trace to get similar quantity. So the idea of obtaining those quantities is that past experience shows that at further analysis, for instance, once you have the white light curve and the spectroscopic light curves, and you start fitting your light curves with transit light curve models, systematic errors in your spectroscopic light curves or white light curve can be removed in some cases by making use of these external data like the full width half max or the position of the spectra on the detector as a function of time. That's the reason why we take those quantities. But there is no guarantee that they will make the miracle and explain the changes or the systematic errors in your spectroscopic light curves. Okay. So we are saving those for the next steps, and we go to step 7, which is extracting of the one-dimensional spectra from the two-dimensional spectra. So what we do here is a simple aperture extraction. I know that there are many different ways of extracting data, extracting spectra. There are packages available in Python for instance, spec-util, so I don't know all of them, but there are which can do, for instance, optimal aperture extraction and other, I don't know, methods. But in this case, what we are showing here is it's a very simple way of extracting. Basically, we just run along the dispersion axis of the spectra along the x direction, and for each column, by making use of the spectral trace information where the center of the spectrum is, this function would place one aperture and would sum the flux inside the aperture. It's a simple summation of the flux. And before it does that, it would also take a user-provided background radius, basically, and would use the background radius to estimate the radius by taking the median and would subtract it from the entire column. So you can see that this subtraction of the median value of each column using the background is occurring several times. So for this specific step, I've opted not to include it, so you can actually just skip it, and because we do it several times, and just run the function that way. And if you do this, it takes also very little time. You will get the extracted spectrum. So here is a plot of one of the integrations where you have the extracted spectrum as a function of pixel column. And next, we load now the wavelength map that we did in the first step. And now we know that to each X column, basically we have an array of wavelengths. So to find the wavelength, we basically just run along the X direction and we take the average or the median of the wavelengths. Now, one thing I need to mention here is that if you plot, for instance, for one column, the wavelength map, you can see that the wavelengths actually vary. They are not the same. And the reason for that is the tilt of the spectrum on the detector. So since these changes in the wavelengths are quite small, you can, in theory, you have mixing basically of individual wavelengths. But since this is very small, the change in the wavelength is very small per column, it's a fair approximation to take the mean or the median. Okay, and now if you do this step, you basically have to each X column now assigned wavelength. And in this way, you're obtaining your wavelength solution. Okay, we can save this again. And once we have basically the spectra with their wavelength solution for each individual element of the time series, we can just produce white light curve by taking the sum of each spectrum along all of the wavelengths. That's why it's called white light curve. And in this way, we will have one flux measurement from the entire spectrum per integration. And we can plot it here. So you can see this way you get very nice white light curve. You can see here different morphologies. For instance, the first morphology is the time that the detector takes to settle into its, say, equilibrium state, basically being illuminated by the star. It reaches another level at which it's basically is stable, and then you can see also the tilt event. So sometime after the mid-transit, something happened, one of the segments tilted, and the collective area, so to speak, of the telescope changed a little bit. So that's the reason why we start collecting less photons and the light curve looks lower. And we can also measure, for instance, what is the average scatter of the light curve. So by taking about 100 points, you can see it's about 160 parts per million. This is actually very good. And then what we can do is we can go ahead and actually produce a few spectroscopic light curves We can do the spectroscopic light curves with the little function that I wrote here, that we show here. Basically, you can provide a wavelength by basically checking your spectrum. You can say, okay, I want one light curve here, one here, one here, one here, just to see what happens to the spectroscopic light curves if I have this tilt event. And here they are, basically for the individual wavelengths. You can see the jumps, and you may wonder, oh, but are those light curves affected differently in individual colors? And so to do that, you can identify where the tilt event happens, basically which integration number. It's 270, actually, I wrote it here. And if you take that index number, you can then correct the affected by the tilt event portions of the light curves using the out of transit data by renormalizing those sections with the median flux of the out of transit data. And you can see here that at least by eye there isn't like really obvious wavelength dependence, but you can't really say by. This is just the idea here is just to have a quick view of what's happening with the data. You can also take, for instance, differential light curves with respect to one of the light curves, in this case, with respect to the 2.9 microns, to see any color differences. You have to keep in mind that if you take these differences, you may also see color residuals from limb darkening, which is not quite expected at near infrared wavelengths. Say if these were optical observations, you would see the color imprint of the limb darkening. And if you really want to do analysis for the wavelength dependence of the tilt event, you really need to do light curve fitting, which is not covered in this notebook. But at least by eye, it's hard to say, actually. Okay, and then one interesting thing you can do is you can plot also the full width half maximum for the individual wavelengths and see its behavior. And I think it's quite interesting because, for instance, here the colors go from blue, so to speak, wavelengths to red wavelengths, so short to long wavelengths. And you can see that first the jump is the highest amplitude, and then for the next actually it goes lower, and then for the next it goes even lower, but then for the 3.5, which is the next in wavelength, it goes back up, and then for the longest wavelength it goes down. That's very interesting. I don't think that I'm not sure this information would be super useful for detrending, but it's interesting to see how the full width half max changes with wavelength. And then finally, actually, since we have now the extracted spectra for the entire time series, we already have the spectroscopic light curves. So if you take all the spectra basically and you put them in one array, you can actually go ahead and correct with the median value of each spectrum. And if you do that, you will get this nice chromatic light curve map, where you can clearly see the out of transit data indicated. Actually, everything is normalized to unity. So you can see the darker parts of this light curve map correspond to the out of transit data. And then you can see the ingress and the egress are these sections where the dark part starts to become brighter. And basically the bright part corresponds to your transit event. In this color map, I actually included the knowledge for the tilt event and basically corrected the data after the tilt event using the out of transit data. You have the option to actually not correct it, just to see how it looks. And you can see the different levels between the light curves before and after the tilt event. Yeah, and then you can actually go back. And finally, the notebook will just save your data ready for the next step, which would be light curve modeling and obtaining of the transmission spectrum. One thing I finally would like to mention is if you look actually in the transit data, you can hint a little bit even the transmission spectrum, because you can see that one of the basically the data corresponding to the redder wavelengths seems a little darker. So you can kind of see a slope here, which is basically the transmission spectrum just guesstimated by eye. And that's it for this notebook.